Dear all, now let's start. Thank you for coming here to our short but very important online course. So it's a pleasure to have you all here. Hope you will enjoy the course. So today we are having a course which is titled Introduction to Collective Choice in Modern Political Economy. This course became possible due to the sponsorship of Severstal. Thanks for them. And your host today will be Professor Clemenс Puppe. Clemenс is a full professor at Karlsruhe University, Karlsruhe Institute of Technology. He studied mathematics and philosophy, very rare combination, I would say. So he became a specialist in the decision theory and especially in the social choice theory. He's the managing editor of the, top journal in the field, Social Choice and Welfare. So his research interests include certain topics in microeconomic theory, which I hope will be highlighted today. So Clemens, please have, the floor is yours. So please tell, how would you like to have questions? Maybe people can write them in chat or ask directly by unmuting themselves.
Okay, very good. Okay, thanks, Mikhail, for this very nice introduction. I'm very happy to be here. I would be even more happy if I would be in St. Petersburg and could deliver the course as in the last years in physical presence, because I always enjoyed being in St. Petersburg. I'm giving this or related courses for many years now at the European University, and I'm very happy that this tradition continues even in these times. And I'm very grateful that you made it possible to do the course online this year. So hopefully next year we all see in person again. All right. So due to the format, online format of the course, I mean, things will be a little bit different than usual. So please also forgive me if I'm technically not that advanced that everything works perfectly. So at some point, perhaps I will have to try out things. And I know there is this whiteboard function in Zoom. I will try to use it when necessary or when appropriate, but please forgive me if I need some time to figure everything out. Okay, anyway. I would like to start the course with a little introduction of everyone. Now, I don't need to introduce myself because Mikhail did that so nicely. Let me just add the following. He said that it's an unusual combination, mathematics and philosophy. Yes, but actually it is for the topic that we will be discussing in this course. These are very good foundations. I mean, you will see that elections do have a strong mathematical component. I mean, it's just sometimes getting the figures right, getting the principles right in order to understand what's happening in elections. But of course, then there will be the task to evaluate whether a certain election method is good, is appropriate, is good for the situation. And that's, of course, not a mathematical task. That is at least partly a philosophical task, because you have to evaluate the foundational principles of voting, like one man, one vote. Actually, you should think in this course, there are many aspects that come together. And there is this philosophical aspect in what kind of basic principles do we want to adhere to in our society. And if we have decided on that, and that's really a philosophical, perhaps also economical question. Why economical? Because economics is concerned with what is value, right? I mean, how can we find out what are the valuable things in life? I mean, this is at the heart of economics as a discipline. So also this philosophical, economical aspect is very important. But then once you have decided on the basic principles, you should do the math and see whether what you do really reflects those principles, or if something happens that you didn't expect just because of the mathematics involved, right? All right, so having said that, this is part of my own introduction, right? This has always been things that have interested me, and even though I have become an economist, these kind of questions that combine philosophical questions and mathematical questions and economical questions have always interested me. And social choice theory and political economy is one place where this comes all together. And I hope you will share my enjoyment and my feeling that this is really an important issue that we are discussing that shapes a large part of our life. I hope that you will have this general feeling after the course tomorrow afternoon. Just also to say that why I believe it's important. I mean, look at what is happening now in the world in terms of challenges to democracy. I mean, look at Brexit decision. One important application of this theory would be to ask, was it right for the British people to take a one-time vote with 50% of the population being decisive for a decision like the Brexit? You will see in a second that in some sense, theoretically, Brexit decision is the most simple decision that you can take collectively, because there seem to be two alternatives, right? Either leave or remain. And in that case, actually, the mathematics is very simple, but there are more questions. So let me please remind me, if I do not come back to Brexit at the end of the course, please talk to me and tell me you wanted to talk to us about Brexit. So I should not forget Brexit. Of course, one should also not forget about talking about electoral college in the US. I don't know if you're familiar with the system of electoral college in the US, but just to point at this, many presidents, Trump is one, but also Bush Jr. was one, who had less than 50% of the votes in the population. Nevertheless, they had more than 50% of the votes of the so-called electoral college representatives, and therefore they became president. That's a question. Is that a good system to rule a country if you have a voting system that really distorts the proportionality within the population? These are all questions that are, I think, very important. We will talk in some detail about French presidential elections and ask the question, is the system by which French presidents are elected, is that a good system? And many more things. So this was the kind of teaser, right? I wanted to indicate that we are doing something really relevant and important here. But of course, we will do it in an abstract way. So first, we want to understand the basic problem that we're talking about, and that can be formulated in a quite abstract way. But we should always remember the true motivation for all that is that we want to get collective decisions, elections, and the outcome of the elections. We want to get this right. Now, unfortunately, as I said, that was a kind of brief introduction of my interests and the topic of the course. I will not be able to really have a good idea of who are you. And I will not ask everybody of you, 26 people now in the meeting, as I see. I cannot ask everyone to tell a little bit about herself, himself. But Mikhail told me that you come from a diverse set of fields, economists, political scientists, liberal arts, and other disciplines. So that means for me that I will really start from the beginning and not require any knowledge, except, of course, you have to be able to think logically. I try to make the prerequisites for the course as low as possible so that you can all follow. Nevertheless, please indicate anytime if you don't understand something and you have the impression, oh, maybe it's not because I'm completely stupid, because that's rarely the case. Most of the time, it's the teacher who is not able to explain clearly. So please do interrupt me when you have the feeling that I'm not clear about something, or I have forgotten to explain a term or something. Please. You can even unmute the mic. I would say, as a rule, now I prefer that you unmute the mic instead of writing in the chat window. There may be okay, here is how I want to structure the course. I will talk about, and I've prepared slides, I will talk about them, but then I will make breaks for general discussion. And during that general discussion, I will be able to look at the chat window as well. But during my talk, I will not be able to look at the chat window. So if you do have a question during my talk or my delivery of the lecture, please just unmute your mic, say, hello, I am so-and-so, please allow me the following question. And then, as long as this is not too many questions at the same time, I think that should work well with 26. And in the discussion sections, we can use the chat window. Okay, is there any question at that moment? I will do some breaks, but please do not ask me when will the break be. That depends always on how I proceed with the slides and when there will be a good moment to do that. So there will be a break approximately in half of the time, so in about now or so, but I will not be able to tell exactly when. Okay, so now enough of introduction. Any questions from your side, please just unmute your mic and speak up. And if not, I would then start with my slides. Just a second. Okay. All right, so please do tell me if you see now full screen.
Yes, everything's fine. Full screen is set.
Very good. Yes, all right. Okay, so here we are. Introduction to Collective Choice and Modern Political Economy. I want to start actually with a historical overview of the problem. And it is very remarkable that in many fields like mathematics, philosophy, in many branches, we have written documents from the Romans, from the Greek. But in elections, it's different. Although you would think that, oh, democracy, where are the origins of democracy? Oh, that's ancient Greek. Athens was the first democracy, as we learn in school. Perhaps there were democracies before, but we don't have any knowledge of that. So, but if Athens is the birth of democracy, we should have some writings of the Greek and the Romans about it. We don't. What exactly the reason for this is, I don't know. But the first written treatise of elections come from this remarkable person, Ramon Llull. I hope I did the pronunciation right. I hope no Catalan people in the audience. It is a Catalan philosopher, writer, poet, logician, martyr. Actually, he is the founder of Catalan literature and the author of a very famous book, the novel Blanquerna. And it can be said it's the birth of European literature in some sense, because it was written in Catalan and not in Latin. And it is a very interesting story about two persons. You can imagine a boy and a girl. The girl is called Natania, and it's about the love of the hero to Natania. And it is the story of their love. Actually, in the end of the book, both decide to devote all their life and powers to God, and she becomes a nun, and he becomes a missionary monk, traveling also in the north of Africa, where he was actually injured in a struggle because of course the Islamic religion was predominant in North Africa at that time, and so they didn't they were adverse to Christian missionaries, but he was very decided that he wanted to mission Christianity. So he was injured. He came back to I think it was Mallorca where he lived, and he died there because of his injuries. Okay. Anyway, I don't want to talk too much about his personal life. What I want to talk about is this chapter 24 in his book Blanquerna, where it is about Natania, right? The friend of the male hero, and it is believed in the monastery where she is that she would be a good candidate for being the boss, right? I don't know how to say this in English. The first lady in this monastery, abadesa in Catalan, as you can see. I don't know what the Russian word for it would be. Anyway, they have to elect, because there are other candidates, they have to elect who should be the leader of this group of nuns in this monastery. And they think about the way to elect this one person. And without going too much into details, the idea of Ramon Llull is to make pairwise comparisons, right? To compare the different candidates pairwise to each other and ask who would get a majority, okay? So we will come back to that particular method of basing a collective decision of deciding on the president of a society, deciding for the chef of a monastery, deciding for the French president or whatever, deciding by binary comparisons. That's a very important idea. And the first written piece of or treatise where this idea has been written down is this chapter 24 of Blanquerna. Now, later one discovered that actually Ramon Llull had also theoretical treatises about elections. De Arte Electionis was discovered 1937, right? Although it was written 1299, and then Artificium Electionis Personarum, another treatise on how to elect persons, right? The translation of this is the art of electing persons, right? That was only discovered in 1959, and actually a colleague of mine in Augsburg Friedrich Puckelsheim, a mathematician, has worked together with a historian in order to translate and make sense of what has been written there. And I will come back to it in a second. Now, look at this. This was in the year 1299, where this treatise, De Arte Electionis, was written, and then nothing happened. I mean, 100 years, nothing. There is no document, or more than 100 years, there is no document that anyone would have taken up this idea, would have seen that there is a problem in how to elect, until this person here, Nikolaus von Kues, or Nikolaus Cusanus, as he is better known in the rest of the world, in the non-German speaking world. I think he is known as Nikolaus Cusanus, philosopher, theologian, jurist, mathematician, astronomer. I mean, just as Ramon Llull and all these great figures of that time, they were universal researchers, right? Everything they found, they wondered at and tried to make sense of the world in a very universal way. And he was actually asked for advice by the Catholic Church how one should elect the Holy Roman Emperors. Now, you should be actually surprised about that. Wouldn't you have thought that, oh, at that time, there is no question of electing emperors. The son of the emperor will be the next emperor, and if there are more sons, it will be the first son, and so. But that was not always so. And actually, the Holy Roman Emperors were elected, and there was a competition between different states, different regions for becoming the Holy Roman Emperor. But you see that the word holy already indicates that the church has something to say here. And but the church is not one person, but the church is, well, conclaves and what have you. I mean, there is also the problem of, okay, if there is a committee, perhaps ruled or built by church members, by what method should they agree on a candidate for the Holy Roman Emperor? Now, Nikolaus von Kues had a wonderful idea. He said, well, let's do it the following way. Every voter has points that he can, or she can, at that time, I'm sure he, can assign to candidates. Now, the higher in the list, the more points. And then after every voter has assigned points to candidates, let's sum these points and elect the candidate who has the highest total sum of points. Now, you should ask yourself, or you can ask and then should ask yourself, that's an interesting method. What is the relation of that method to the pairwise comparison idea of Ramon Llull, right? And in fact, it turns out these methods are very different, but they are still, well, they are very different methods of electing. And to the present day, these are the paradigmatic methods among which there is great discussion which one is better. The point summing method of Nikolaus von Kues or the pairwise comparison method of Ramon Llull. Now, interestingly, this history has been forgotten for a long time, and it was really, among others, my colleague Friedrich Puckelsheim from Augsburg, but also, of course, others, who rediscovered that this question I was just posing, which is nowadays known as the struggle between Bourdin and Condorcet, is much older than this struggle between Bourdin and Condorcet. But I'm going ahead. Let me tell you about Bourdin and Condorcet. Now, one very important moment in the history of social choice and the history of how elections were made was a struggle between two men in the French Academy of Sciences. It was Jean-Charles Chevalier de Bourdin, who was the secretary of this society of the French Academy of Sciences. He was a mathematician, a military engineer and sailor. That's why you see him here in this picture. To be fair, nobody knows whether this picture really shows Baudin. It is not known whether there are any pictures of Baudin, but at some instance, this was shown as a portrait of Baudin, and since then nobody complained about it. But actually, the evidence that this, what you see here, the picture, is really Baudin, the evidence is very small, actually. But the point that I want to do is that he thought of the method by which the French Academy of Science would admit new members. You can imagine that the French Academy of Science has exactly that problem. The art of electing persons is very relevant to the French Academy of Sciences, because, of course, whenever you're admitted to the French Academy of Science for a lifetime, but sometimes members die and have to be replaced by new members. Now, how do you do that? There are, of course, many candidates. Many researchers would have wanted to become member of the French Academy of Science. That's a wonderful honor to be there. So there were many candidates for each slot, for each available slot there. And the question is how to elect them. Of course, the French Academy, the members would say that, okay, it's our right to determine the new members, but how do you do it? And they did it by a method called Plurality Rule, which is very simple. Everybody gives one vote, every voter gives a vote to a candidate. The candidate with the most votes is elected. This is known as Plurality Rule, and it was used by the French Academy at that time. And as you will see in this course, this is a very bad method of election, that you just give one vote to your favorite candidate, and the candidate that receives the most votes is elected. Now, Baudin made a counter proposal, and this is now known as the Baudin count. And here I want to give you the first serious example. Why would you think that one needs to think about voting and elections? Suppose, very stylized example, suppose the French Academy would consist of 9 members, let's say, 4, and there are 3, here are their rankings. I hope you see my cursor, or 4 voters in the French Academy. There are 3 candidates, A, B, C, and 4 voters would prefer candidate A to B to C. That's how you should read this column here. It is indicating the preference ranking of, in that case, 4 voters among 3 candidates. So these 4 voters agree that A would be the best candidate, B the second, C the worst. Another 3 voters would think that B is the best candidate, C second, and A last. And another 2 voters would think that C is the best candidate, followed by B, followed by A. Now, as I said, Plurality Rule would simply do the following. It would count the first places that a candidate has here. So candidate A has 4 votes for herself. Candidate B, 3 votes. Candidate C has 2. Candidate B has 3. So who wins? According to Plurality Rule, the plurality winner is A. Okay, A gets 4, B gets 3, C gets 2 votes, and that's it. But notice why this is not the good thing to do here. And it's very clear and it's very obvious that you should not choose A in this case. Why? Because there is a majority of 5 people, namely these 3 voters and these 2 voters, who think that A is the worst candidate in this case. Okay? So if you would simply apply plurality, you would elect a candidate, A, who would be considered the worst candidate by a majority. And this is, well, this is a problem, I would say. And Baudin said this is a problem and tried to convince his fellow members of the academy that this is a problem. But what kind of method would be suitable here, and what kind of method would prevent that A is elected? Well, it's Baudin's count or Baudin's method. And as I said, Baudin suggested the following: give points to each candidate. And if the candidate is high in your ranking, which means you think it's a good candidate, then give more points. So concretely, in the case of 3 candidates, we should give 3 points, namely 3 to the best candidate, 2 to the second best, and 1 to the worst candidate. And then after each voter has given points, then we sum over all points given by the voters to candidates. Now let's do this here in this case. And what do you get? Well, 4 voters give A 3 points. That means 12 points. I'm sorry, where are we? A. 4 voters give 3 points to A. And then 3 voters give 1 point and 2 voters 1 point. So for A, what you get is 4 times 3, 12, plus the 3 points of these 3 voters, plus the 2 points of these 2 voters, makes in total 17 points for A. C gets 4 times 1, 3 times 2, and 2 times 3 points, which makes in total 16 points. But now look at B. B gets 4 times 2, plus 3 times 3, plus 2 times 2, and that makes a total of 21 points. And if you look at the rankings, you see that B is actually the natural, what you could call compromise candidate, right? B is never worst, right? For no voters, B is on the last rank. For some voters, it's first, not for the majority, because only for 3 voters. But then the other 6 voters find that B is at least in the middle and not worst. So B here is a justifiable choice. And it is the Baudin winner. And that's what Baudin suggested. That's the famous Baudin method, which is used to this present day. But then, of course, it's not the only way to solve the problem. And the counter proposal came from the successor of Baudin at the chair, at the secretary chair of the French Academy. And this is this guy here, Jean-Antoine Nicolas de Caritat, Marquis de Condorcet, a very famous French philosopher, mathematician, but mainly he was not only political scientist, he was political activist. And he played a major role in the French Revolution and was actually on the side of the anti-royalists in the beginning. But then during the development of the French Revolution, he turned against the violent policy of Robespierre and was then put into prison and died in prison under unknown circumstances. Some people believe that he was killed actually in prison by his political enemies. What I want to tell you before I come to his theory, I want to tell you that he made very important contribution in political economy, but also in politics itself. He was one of the first defender of the right for women to vote. Right? So he not only not only thought theoretically about the problem, he really was active in changing and improving things in the political sphere. Now, his most famous contribution to the theory of voting is this writing here, the Essai sur l'application de l'analyse de la probabilité des décisions rendues à la pluralité de voix. And here, if you know a little bit of French, pluralité de voix is, of course, the translation of this is plurality rule. But in fact, he was analyzing this quite extensively. And actually, the method that he proposed is not plurality rule, although you could think so by simply translating this title here. Now, here, let me tell you how Condorcet challenged Borda. A very simple example again, it's an abstract example, but you can imagine many stories, many contexts in which something like that happens. This is the simplest example that you can construct to illustrate the problem. Suppose there are again 3 candidates, A, B, C. There are 5 voters now, 3 of which think that A is best, B is second, and C is worst. 2 voters think B is best, C is in the middle, and A is worst. Now let's calculate the Borda winner. It's very simple. Why? B is, because you simply multiply 3 times 3 for A here, plus another 2 points for A here, makes 9 plus 2 is 11. What about B? Well, B gets 3 times 2 is 6, and then 2 times 3 is another 6, makes 12. So B is the Borda winner here with 12 points against A, who only receives 11 points. But now suppose you elect B, and then comes A and says, listen, there is a majority of you, namely 3 voters, who actually prefer me as a candidate, right? There is a 3-2 majority in the comparison of A and B that would say, let's rather have A than B. But Borda nevertheless selects B. Now, this is the point where you should now really think of this, something deep. Although this is a very simple example, I think it is a very deep, a very deep problem is hidden here in this very simple example. Because in this example, you can still say, as we said before, we could say that B is the compromise candidate, right? Yes, many people, a majority even, say that A is the best candidate. But the minority of 2 voters say A is worst. So A somehow polarizes the society. A little bit more than half of the society think A is best, but the rest thinks A is worst. Now, contrast this with B. Well, B is best for this minority, but the majority of 3 voters thinks that B is acceptable. But now notice that when I was making this argument, talking something about polarization, acceptable, I am really putting more information into what you see than what you see. You simply see that 3 voters say A is better than B and B is better than C. And 2 voters say B is better than C and C is better than A. Now, if we want to stick to that information, right, and no other information, mustn't we then say that we should elect A? Because this compromise argument cannot be made without talking about how B, the middle candidate, fares in comparison to the best and the worst candidate. So it could be, for instance, that these three voters say that, oh, B and C are extremely bad with a slight advantage for B, right? And these two voters say, oh, all three candidates are okay, with a slight advantage for B over C over A. But we really don't care so much about B, C, A. If you press us, if you ask us, you must give a ranking, then we would say, well, okay, B is a little bit better than C, and C is a little bit better than A. And if these three voters then say, if you ask us, B and C are completely disastrous candidates, the only candidate that we can imagine is a good candidate is A. In that moment, B cannot be considered a compromise candidate. You see, whether B can be considered a compromise candidate depends on more information. We economists call this information cardinal utility information. You have to say something about where in this ranking or in this goodness scale between the best and the worst candidate, where is the middle candidate? Is it more to the better or more to the worst candidate? But if you refrain from using this information, and actually this table does not give any such information, then, and that's now Condorcet's argument, you should go for candidate A. Why? Because a strict majority of 3 against 2 voters prefer A to any other candidate. Actually, notice that A is not only preferred to B by a majority, but A is preferred to C as well by a majority, actually by the same majority of 3 voters. And such an alternative is called a Condorcet winner after Condorcet. So the Condorcet principle would be, if there is a candidate that is preferred, now listen carefully to my words, if there is a candidate, in this case it's A, that is preferred by a majority to every other candidate in a binary comparison, that candidate must be chosen. Notice such a candidate must necessarily be unique, because right, this candidate should beat every other candidate by a strict majority. So it must be unique, and it seems to be a good principle to choose such a candidate. Notice, I want to make an even stronger argument now for the choice of the Condorcet winner, namely, look at B and C. If you look in this table at B and C, you see that all voters, namely all 5, think that B is better than C. Now, suppose you are in a within your family, right? You're voting. Let's say these are the 2 parents and 3 kids, right? These are the 5 people, and you want to know which restaurant to go to for lunch, let's say, or 5 students. You're voting on the restaurants for lunch, A, B, C. And now somebody says, oh, look, we all find B better than C. So restaurant C should not even be voted on the ballot, right? C is inferior for all 5. So the restaurant C is beaten by B for all 5 students or the members of the family. So let's simply erase C. Okay, why do we list C here in these rankings? Let's just erase it. But if you erase it and you see the reduced problem where you only have A, B, what you get is 3 voters prefer A to B and 2 voters prefer B to A. And then even border rule says choose A, because A gets 2 points and B gets 1 point from every voter. Right? I mean, the first ranked alternative gets 2 points from every voter. The second gets 1 point. And if you do the border calculation in the reduced problem without C, then A becomes the winner. But before, in the presence of C, B is the border winner. Now, this is called in the literature an irrelevant alternative. So C is present here, it has no chance of being elected, but it influences the result. And this is sometimes, well, this is called a violation of the principle of the independence of irrelevant alternatives. C should be irrelevant for the choice, but nevertheless, whether C is present or not affects the election. So I have now tried to make the strongest case for the Condorcet winner that I can make, but now comes the bad news. Namely, oh, I'm sorry, here comes the bad news. The Condorcet paradox. Namely, there are cases in which Condorcet winners do not exist. And this actually was already seen by Condorcet himself. That's why it is called the Condorcet paradox. Now, it is very simple. Suppose there are 3 voters. They have the following rankings. Candidate A is best for the first voter, B second, C third. For the second voter, B is best, C second, A worst. And for the third voter, C is best, A second, and B worst. Now do the binary comparison. We have to, in order to find the Condorcet winner, we have to compare any pair of candidates and ask ourselves who is the winner. Compare A to B. This voter votes for A and this voter votes for A. So A is preferred to B by a majority. Compare B to C. This voter here, the first one, and the second, they both prefer B to C. So B is preferred to C by a majority. And C is preferred to A by the second and the third voter. So C is preferred to A by a majority. Which means that there does not exist a Condorcet winner. Because remember, a Condorcet winner is an alternative that beats every other alternative by a majority. But here we have a problem. Every alternative is beaten by some other alternative in a majority comparison. A is beaten by C, C is beaten by B, and B is beaten by A. So you have what is called a cycle, a preference cycle. There does not exist a Condorcet winner. And the method of pairwise majority voting, remember, that was invented by Ramon Llull in his Blanquerna novel. This method cannot be applied in this situation because you cannot choose any alternative if you want to stick to this pairwise majority criterion. Just a second, I have to take a... Okay, let's think. So what is the solution? Well, there has been one proposal actually, which is as follows. Well, if there is a Condorcet winner, then choose the Condorcet winner. And if there is no Condorcet winner, like here, then use the border rule. But this is quite ad hoc actually, and it's not clear whether this really solves the problem. Before we enter further into this issue about which is the right voting method, is it one that is based on Condorcet winners or the border rule, let us step aside for a second, and I want to show you the following. Remember, in this example, which we just had here, if you delete C, then there are only 2 candidates left. And I have argued that if there are only 2 candidates, then here the majority winner must also be the border winner, right? Actually, that would be a kind of small exercise for you at home, right? After the course, perhaps you want to think about the question or the problem. Prove to me that when there are only 2 alternatives, then a Condorcet winner must be the border winner. But when there are three, in the moment where there are three candidates, this is no longer true. Because as you see in this example, the border winner is B, but the Condorcet winner is A. So you see already in this example that the border rule sometimes does not choose the Condorcet winner, even though it exists. Okay? But this cannot happen for two alternatives or two candidates, right? I will use the term candidate and alternative interchangeable, right? These are the same. Candidates and alternatives are the same thing for this course, okay? Because, yeah. When there are only two candidates for election, then there is actually a unique, a single best voting method, unless, remember Brexit, unless you have more information about the candidates. So if these two candidates are neutral, as we say in voting theory, so you don't want to give one candidate an a priori advantage over the other candidate, right? So they are on the same footing. And if the voters are all on the same footing, that is called anonymity. That means more or less one man, one vote, or as we should say in these times, one woman, one vote as well, of course, one person, one vote, perhaps. So if you have this principle of one person, one vote, actually you should think about the question, if you have one person, who is a person? That's an interesting question to think about. There are people who, well, for instance, children. Are children, should they allowed to vote? And at what age? There are people who defend that everyone should be allowed to vote, right? Every kid, no matter which age, should be allowed to vote. If you think that this is absurd, the counter argument is you cannot determine one age for everyone where you should have the right to vote. And the hope is anyway that people will vote only if they are reasonably informed. So you can be pretty sure that a small kid will not vote because it does not really have information there. Anyway, this is a side question, but I think it's an interesting question. Should KI agents have a right to vote? They are well informed. Anyway, if you rule out all these considerations and say, well, okay, let's assume we have a predefined electorate, right? We don't want to discuss the question who should be able to vote, then anonymity means for a given set of voters, every of this fixed set of voters should have one vote. That is called anonymity. And it should not matter who votes in which way. That's called anonymity. Everyone should have one vote, and it should be invariant with respect to a permutation of agents, right? That's technically the anonymity condition. Neutrality means you don't want to give one of the two candidates an a priori advantage. That means neutrality. And positive responsiveness means that if one candidate wins and now a voter changes his mind who voted for the other candidate and even votes also for the winner must stay the winner. That's called positive responsiveness. We will talk about that property later in the course. And this guy here, Kenneth May, showed in a very influential paper that is mathematically very simple, but it is very influential because he showed that these three conditions alone are enough to guarantee that the two candidates are chosen by simple majority. Okay, so notice that simple majority in the case of two candidates coincides with many voting methods that are different for more than two candidates. For instance, border is just simple majority with two candidates. Plurality is also the same with two candidates. So with two candidates, really most of the voting methods collapse to one single method, and that is called simple majority. You simply count which candidate got more votes, and that's it. And this is, in this abstract model, the only reasonable election method for two candidates. But the problem comes in as soon as you have more than two candidates, as soon as you have three candidates. Okay. Now, so this is the state of play around the time of the French Academy of Sciences, when Bourdin and Condorcet struggled over the right voting method. Now, and this is a side remark, but I find it very, very funny. This was an intellectual highlight, I think, in the history of well, election theory, but perhaps even beyond election theory, political economy. But what happened then? Well, Napoleon became at some point the secretary of the French Academy of Sciences. And what did he do? By decree, he said, we go back to plurality rule, ignoring all the intellectual progress made by these two wonderful persons, Bourdin and Condorcet. Napoleon just ignored all that and switched back to the bad method of plurality rule. Just a side remark. What happened then? Well, again, a long time, nothing happened in the history of social choice. The controversy between Bourdin and Condorcet was soon forgotten. The French Academy switched again back to plurality voting. And only in the year 1883, a mathematician called Nansen published the first systematic comparison of voting systems, and actually developed also his own method, the so-called Nansen method. We will probably not have time to talk about it, but let me just mention to you, the Nansen method is a very clever method that turns out, however, to violate this very fundamental principle that I just mentioned. You know, this positive responsiveness. Remember, this is the condition that says, suppose I have a winner of an election, and then some voter who voted not for the winner now votes for the winner, then the winner must stay the winner. Right? This principle is very basic. It's called positive responsiveness. Notice that it sees that a voter would like to give his vote. Suppose that I was not sure whether by voting for someone, I increase the chances of this someone to win the election, then perhaps I would rather want to stay home instead of electing for my preferred candidate. So a violation of that positive responsiveness is a very serious problem. And actually, unfortunately, this Nansen method, which sounds very reasonable in the first place, was found much later, not by him, much later, to violate this positive responsiveness. And that's why it's not a good method. Actually, this guy here is Nansen. You see a very respectable, honorable man. Probably here, this is in somewhere and at a British university. I think he was then living in Australia, but I'm not sure at the present moment. Okay. Then the next interesting move was by a mathematician named Dodgson. Perhaps some of you know this person better under the name Lewis Carroll, which was his pseudonym, and he published the famous Alice in Wonderland books. But in fact, he was a mathematician, and he also devised a method, the so-called Dodgson method, which shares with the Nansen method the following feature. They select the Condorcet winner whenever it exists. But in other cases, when the Condorcet winner does not exist, they do something clever. But it turns out what they do is not clever enough. So in the end, there is a problem with both of these methods, because I don't want to go into details here. That would be way too detailed for this course. But you can prove that both the Dodgen and Nansen method, they sound very reasonable at first, but if you examine the mathematics behind them, they are problematic. And they are problematic in particular because they violate this positive responsiveness. All right, now, again, 50 or even more years later, now something happens, something very important, namely Ken Arrow, the Nobel Prize winner in economics. And some people say that he could have won more than one Nobel Prize because he made so many important contributions to economics that he would have deserved to be awarded at least 2 Nobel Prizes. And actually, the Nobel Prize that he won at that time was mainly for his contribution in general equilibrium theory and the proof that general equilibrium, economic equilibrium always exists. But this, what I want to talk about is at least as important as a contribution. It's one of the most fundamental results in all of the social sciences, in my view. And it's based on his dissertation. And he asked the following question. And the question, remember, comes really from from 2 examples that we already had. The first one is this here, Condorcet Paradox. What do we do when majority voting gives us cyclical majorities, right? You remember this example here. A is preferred to B, B to C, C to A again, and A to B. And so we are cycling here and we cannot really choose. But there was another example, namely this example here, which said that if there is an irrelevant candidate, which was C in this example, that candidate should not influence the result. Right? Now, Arrow asked the following question, which we can now almost formulate precisely. He asked, is there a method that would be independent of irrelevant alternatives, right? So we have to formulate that, of course. What does it mean precisely to be independent of irrelevant candidates? And at the same time, never lead to such cycles? And the answer is very surprising. If you look at this in this generality, again, look at this question. Is there a method so that irrelevant alternatives do not influence the result, and such that the method has never the problem that occurs here in the Condorcet paradox, so that you cannot choose a candidate because for each candidate there is another candidate that is collectively by the group preferred to that candidate? The very surprising answer is there is no such method, right? And I will come back to this in very much detail this afternoon. This afternoon, I will probably prove to you this theorem. And the theorem is called the Arrow theorem. And it says that if there are at least 3 alternatives, remember, for 2 alternatives, we do have a good method, namely majority voting. Majority voting is, of course, never runs into cycles with 2 alternatives, because with 2 you cannot have a cycle, and it cannot be susceptible to the influence of irrelevant alternatives, because with 2 candidates, every of them is relevant. Okay, but with 3 candidates, the theorem says there is no method of aggregating into individual rankings into a social ranking that can always be applied, that means universal domain, that is non-dictatorial in the sense that we do not declare one individual as the one who always decides what will happen. It respects unanimity in the sense that if everybody agrees that B is better than C, C cannot be chosen. Notice that is here. everybody agrees here that B is better than C, so then C cannot be chosen, and satisfies this independence of irrelevant alternatives. The theorem says there is no ranking that satisfies these four basic desiderata of a social choice rule. This is a very negative result, and because it really poses a problem to us as the as those who think about the question, how should society be organized? Actually, the question here is really, if you write the constitution of a state, what should you write in there when it comes to the question how joint collective decisions should be taken? What would you want to write there? Well, Arrow's hope was that by formulating such fundamental principles, he could perhaps shrink down the possible ways in which societies should take their collective decisions. I mean, it would be extremely an ideal world if these fundamental principles would pin down one rule. Let's say, as in the case of two alternatives, where you say, well, very fundamental principles pin down one way of electing, namely by a simple majority. But that works only for two alternatives. And there is no such counterpart for three alternatives, as the theorem shows. So it is not only that some things are ruled out, no, everything is ruled out. And this is really a problem, because now you should think about the question, what should we write down in our constitution? I mean, almost every country has an electoral law. I mean, Germany has, and I know a bit about it. The US has electoral college. And what the Arrow theorem says is every such electoral law must violate one of these fundamental conditions. And that's a problem, because they have really something to it. We will come back to these conditions, and I will discuss in even more detail in the afternoon. Okay, but it becomes worse. Okay, so you think that, okay, one negative result, let's think how to solve the problem. No, it is more problems coming up in voting theory. Namely, if we are in a voting context, okay, I should explain this. Arrow sought to aggregate individual rankings into a social ranking. So the exercise that Arrow did was not only choose one thing, but for the group or for society, but determine what is best, what is second best, what is third best, also for the group. So the input here in such an Arrow exercise are individual voters' rankings, and the output is a collective ranking, but it's again a ranking. Now, we speak of a voting context when you don't require that the group or society has a complete ranking. For a voting context, it's enough that society chooses one thing. Okay, so there is a very close relation between the two contexts, and if you're interested, we can talk later about it. But if you are in this voting context, then you can show that this a counterpart of this independence of irrelevant alternatives and the positive responsiveness condition is closely related to the following condition, which is very interesting, and it's called strategy-proofness. And strategy-proofness means that no voter should have an incentive to lie about her preferences. And that's actually a very important requirement, because suppose that it's not in my best interest to tell the truth about my true preference between candidates. But that I find that, oh, wait a minute, we are using plurality rule or border rule or whatever kind of rule. I prefer candidate A, but in fact, A has no chance of winning because I know something about the preferences of the other people. My best candidate has no chance of winning. Therefore, I vote for my second best. Now, this might be individually rational, but for a social evaluator, for someone who wants to guarantee good outcomes, this is disastrous. Why? Because if I don't give my true preference, I vote for my second candidate, perhaps the other voters also vote only for their second candidate, and then my guess about what they would do is wrong, actually, and I voted for the wrong candidate, and in the end, it could happen that a candidate is elected that very few people really wanted to have elected because of these strategic manipulation going on in the voters. Now, the natural question to ask is there a voting rule that prevents this incentive of manipulating the election? And again, with two candidates, A, B, the answer is yes, there is a good voting method that prevents strategic manipulation. It's majority rule among two candidates. So let's, just as Arrow asked, can we have this also for three candidates? Can we have this for three candidates? And the answer is no, we cannot. The famous Gibbard-Satterthwaite theorem, proved some 20 years after the Arrow theorem, says that if you have at least three alternatives and you want to have this strategy-proofness, right? That means robustness against manipulation, and you have this respect for unanimity, then there's only one way of preventing, there's only one thing left, and the one thing left is declare one voter the dictator. Declaring one voter the dictator means that not only in a particular situation, what will be elected coincides with the best alternative of some voter. No, it means that in any situation, the rule says voter number 17 is the only decisive individual. So we will always choose what voter number 17 finds best. That's a dictatorial rule. So, and since you don't want to have dictatorship, that's not democracy, right? I mean, that's then we are no longer talking about democratic decisions. If in fact only one individual makes the decision, then we are not in a democracy because we can forget about all other voters. It only depends on one voter, which is far from our notion of democracy. So if you want to don't have this, you want to have three alternatives, then every election, that's what's said here, down here, is a strategic game. And actually a very complex game, because in order to determine my optimal strategy, I should somehow have a belief about the behavior of the other voters. So this is really, again, a very negative result, and we should worry about this result. And especially as economists, we should worry about it. Because now it's the question of game theory to predict the outcome here. And we know in game theory that you can have many situations where the outcome of rational play is socially bad. This is well known under the heading of prisoner's dilemma. And I think you have heard of this problem. And it is a problem in voting as well. And we will see examples for this later in the course. I am still in the overview part. Let me just have a brief look at the clock. So I will go on for 10 minutes, and then we will have a 10-minute break and go more into detail. All right, here comes the first good news. Finally, some good news. The so-called median voter theorem. I will have to go back here. There has been one condition here, the first one, called universal domain. Universal domain was Arrow's requirement that we should be able to apply our voting method under every possible circumstances. And that's justified because he asked himself how to write a constitution. What should we write in our constitution as the method by which our society should make decisions? But if we leave this constitutional level, right, this very abstract model, and come to smaller problems where we know perhaps something more about individual preferences, perhaps then we can do something. And that is indeed true. And this is called the median voter theorem. Suppose that you can put the candidates or the alternatives into a spectrum from left to right. The important thing is that this should be one-dimensional, right? Suppose you can order the candidates A, B, C, D from left to right in a one-dimensional spectrum in such a way that every voter has what is called single-peaked preferences over the candidates, which means that there is one most preferred candidate, and the further you move away, either to the left or to the right of this candidate, the worse the candidates become. So if that is the following condition, notice that if C is your best candidate, then necessarily, of course, C must be preferred to every other candidate because it's the most preferred, but you know something as well, namely, you know that B must be better than A for this individual. Why? Because A is even further away from C than B, okay? And to the right side, the same thing. Someone who has C as the most preferred candidate must also say that D is better than E. Why? Because E is even further away from the peak C. That is called single-peakedness. And if every voter has single-peaked preferences, then you can show, and actually this is not difficult, that pairwise majority voting can never have these cycles. Pairwise majority voting really works well here. And if you have an odd number of voters, then how do you find the majority winner? It's very simple. For an odd number of voters, here we have 3, you simply look where is the most preferred, the top candidate for these voters, and you choose the median of these peaks, okay? So here in this case, C must be the majority winner. The logic behind this is very simple. Why must C be the majority winner? Well, if C is the median top alternative or the median peak, compare C with anything to the right. Well, since C is the median, you know at least half of the people are to the left of C, including C. So they all vote for C against D and E. So against any alternative that is to the right, you will get the majority of those people to the left. And why is it a majority? Because this is the median peak. And the same is true when you compare C to an alternative to the left. Again, now you get a majority, but now, of course, the majority is the majority to the right of C, including C. And again, because C is the median, this is in fact a majority. So this was actually independently discovered by Duncan Black and Arrow himself, who also saw that this would be a way out of his problem. Because, you know, this solves both problems. It solves both the Arrow problem and the Gilbert-Satterthwaite problem, because now majority voting yields a consistent ranking, right? So you simply take pairwise majority voting, and if all voters have single peak preferences with respect to a particular spectrum from left to right, then you can take majority voting both as the collective ranking and the peak as the collective choice. Notice this is a widely applicable model, because you could think of this left-right spectrum as a political spectrum. A is the leftist candidate, E is the rightist candidate, and the other candidates are in between. And you assume that every voter has a position in this political spectrum, and the further you go away from your position in the political spectrum, the worse for you as a voter. So this is a very natural model in the political sphere, but actually not only in the political sphere. Here I give you another example. Suppose it's about the temperature in the room. There are many people in the room, they have different preferences of the temperature in the room, but you have to set the heating at some temperature. And then you would simply say, well, you ask the people, what is your preferred temperature? And you'd set the temperature on the median announcement, because a majority would like to have it warmer than the median and the majority colder. So this is the natural compromise in this model. So this seems to be really a good model for some purposes, but of course not for the Constitution. Why not? Well, you cannot write in the Constitution, oh, let's assume that we all have single peak preferences and then we use majority voting. Why can you not do that? Well, because there are some cases in which you do not have single peak preferences. I only claim that there are natural cases where preferences have this structure, which is shown here, but there are also many cases in which this structure simply does not apply, because some voter would say, my preferred alternative is A, and my second best is E, right? I do not want to be in the middle, either A or E. That is, of course, not single-peaked. Why? Because this is kind of extremist preference, but that is not something bad. Suppose we are talking about, I don't know, let's say military technology, right? A country has to decide on military technology. No, better example, energy policy. You can have preferences for nuclear, natural resource, for resource minimizing energy forms like light and water energy, and can put all your resources into such a technology, or in nuclear power plants, but you don't want to have a mix of them because you think this is not efficient, something like that. I'm now thinking it's not such a good example. Let's say military technology. You could either have conventional arms or nuclear arms, and you could well have a preference for having all the resources for one of these categories and not for some middle category. Anyway, what I want to say is simply that preferences need not be single-peaked. If they are single-peaked, then this median voter theorem gives you a very good way to decide. But it's not a universal thing like Arrow wanted it to have. Let me just note, and now I go very quickly to the rest of the slides, just to give you a flavor of the research that is going on. You can generalize this notion of single-peakedness very much. So you can formulate some kind of single-peakedness condition, not with respect to this very simple graph, right? Notice that this line is simply a graph. You could consider general graphs and require single-peakedness with respect to graphs. And you get also possibility results, but not always. And the question is, for which graphs do you get possibility results? For which graphs do you get impossibility results? That's a very active area of research to which I have contributed with Klaus Nehring, my long-term co-author. Here is one thing that is interesting to note. You could argue, well, okay, if you have cycles, right, with majority voting, why not avoid the problem and say that, well, we do the pairwise majority comparison in a certain sequence, okay? And then at every step where we do a pairwise majority comparison, one candidate drops out and we choose the candidate who stays, who remains until the end. Isn't that a very natural way of doing sequential majority voting? Yes, but what is the problem? The problem is it depends on the sequence in which you do the binary comparisons. The result will be dependent on that. And even it could be a very bad candidate that remains. And here is this simple example. Now we have 3 voters and 4 candidates, A, B, C, D. You see the rankings of the 3 voters here. And this is the so-called majority tournament graph. And the interpretation is very simple. An arrow from B to C means that in the binary comparison between B and C, a majority prefers B to C, which you can see here. B and C B is preferred to C by this voter to the left and by the voter to the right. So B receives a majority. And if you now compute all the majorities, notice you have to have 6 arrows here, because with 4 candidates, you have 6 binary comparisons. And you see the arrows here are like this, and you see there is a cycle. A is preferred to B, B is preferred to C, C is preferred to D, but D is again preferred to A. So you have a kind of Condorcet paradox here, but now let's say we make the binary comparison in a certain sequence, and then we simply delete a candidate. So for instance, if we begin with A against B, A wins against B, so B is deleted, right? So A remains. So then we compare A and C, then we see A is deleted by C. So A is deleted, C remains, and then we compare C to D. C deletes, D is beaten by C, so D is deleted, the winner is C. But notice, if I start with D, of course, we get another winner. If we start with C, we get still another winner, and so on. And actually, there is a sequence here who does something very bad. Namely, suppose we first compare C versus D. If we compare C versus D, D is deleted. B to C, then C is deleted, B remains, and then we compare B to A remains, so A is elected. Now, is there a problem? Yes, there is a fundamental problem, namely look at D and A. If you compare D with A, every voter would prefer D to A. But you have chosen A, although every voter prefers D. So this is what is called A is an Pareto inefficient alternative. There is something that everybody prefers, and so we should not choose A. Actually, this is one of Arrow's principles, one of fundamental principles. You should not elect a candidate such that there exists another candidate who is preferred by everyone. Okay, so this is a violation of this so-called unanimity principle. And therefore, sequential majority voting does not solve the problem. Okay, you can refine the analysis, and that has been done.